This is the last class on Von-Neumann algebras. Maybe we'll have one or two classes on six-star algebras again. Last class on Von-Neumann algebras. So today we want to discuss two infinity factors. Okay. So for that I state the following theorem, which I will not prove. Unfortunately, I would assume I will be using it. Okay. So this is M is a finite Von-Neumann algebra. I mean, it's involved and it takes time and it's messy, and if we had a course on Von-Neumann algebra, I would have proved it, but I mean, this is not exclusively on that. So let's assume I will be using it to prove for two infinity factor. M is a finite Von-Neumann algebra, then there exists, then M admits a trace. That's all. We know the other way is true. If it admits a trace, it's finite. That we have proved. Okay, by considering, I mean, yeah, we assume. Yeah, we are going to assume it. We earlier we didn't use it anywhere. Yeah, we proved that Tomita-Takasaki theorem for a 2-1 factor with a trace. That's right. With that, we assumed it comes with a trace. We didn't use it. I mean, yeah, when you have a trace, you can do that, but it actually, there is a trace. Okay. So we didn't, but to prove whatever I'm doing, it is needed. Okay, so that's what I'm saying. So this is true, which we used it. I mean, the theory which we developed is based on trace. Of course, it's based on trace, and using the trace only, we define that operator J. I mean, J is anti-unitary because of the trace and other thing. But we can restrict to that situation and prove that here I have to use it. Okay, so it's just because something more. I mean, something about two infinity factor. Further, I need. So, but you can imagine how this is proved. See, when we have a trace, we got something called a dimension function for a projection. For example, if you take Mn, then the small trace is summation trace of any matrix X is equal to summation Xi I 1 by n. And then the trace of 1 will be 1. You have to put this 1 by n. So in this, if you take any minimal projection with respect to this, any minimal projection will trace 1 by n, right? 1 by n. So trace will be dimension divided by n, dimension of the projection, dimension of the range of the projection divided by n. In B of H also you can do this, but B of H, the trace of identity will be infinity. So, but you can restrict to what are called trace class operator, which you must be knowing by now. Okay. So for trace class operator, you will have the trace. But trace class operators are dense in B of H in the strong topology, not in the norm topology. Norm topology, it will be dense in compact operators. Okay. There are something called compact operators. They form a C-star algebra, which doesn't have an identity when H is infinity. So that will be C-star algebra. And I mean, what I'm saying is trace can be defined on a dense subalgebra, which is strongly dense, okay, not in the norm topology, strongly dense. So similar, if you have a 2-1 factor, then if we have a trace, then we can define a dimension of a projection. It's just trace of that. So this you have to do the other way, which is more involved, of course. So you have to develop a dimension function on this 1 factor, and once you define it on projection, you have to extend it to all of them. Okay, so that requires something. So yeah, is it subgroup? No, you don't need K theory for this. I mean, this is just direct. You can refer to Dixmeyer, or you can book by Dixmeyer, or you can refer to the book by Sundar, which is much simpler, by Invitation to Von-Neumann algebras. Okay, you can look at that. And it was a book written in the early 90s, late 80s, 89 or 90, I'm not sure. Okay, but the notation is, I shouldn't say it here. I mean, it's a bit messy. We are not following that notation, but but if you really are interested in it, you can look at that. Okay? That has a better proof. Our Takasaki book is there, which there are 3 volumes. If you are really interested, you can read that. I would suggest if you are going to work on operator algebra, then you can do that. If you are working on some other area, then you need not look at Takasaki book. Okay? So we are assuming this, then things are simpler. Okay. So we want to prove the following fact proposition. We assume M is a type 2 infinity factor. Because finite means 1 is a finite projection. Type 2 infinity means it contains finite projection. There are some finite projection, but identity is not the finite projection. Identity is equivalent to some proper subprojection. So this is not a finite. This is not a finite factor. This contains finite projections. Okay. Then and it contains finite projection. So there exists a P in M finite projection. Okay. Then there exists a family Pn. All Pn is equivalent to P, so that makes it finite projection. If it is equivalent, that should be finite projection. Okay, and summation Pn equal to 1. Of course, whenever I write summation of projection, it's in the strong topology. Okay? Infinity. It's in the strong topology. So proof. So use Zone's lemma in the usual way and vector. Huh? Yeah, countable collection. Huh? What is the question? Will it be countable or finite, you are asking, or uncountable? Huh? Uncountable, not possible because we are separate Hilbert space. You work with separate Hilbert space. Sorry, separable Hilbert space. In separable Hilbert space, it has a countable orthonormal basis. So you cannot have uncountably many. Sorry, I didn't say, forgot. Sorry. Pn is orthogonal to Pm. No. Sorry, I should have said this. I forgot to say. Yeah, N is, I mean, otherwise there is no point. I mean, this thing will have a problem. I mean, this is, they are orthogonal projection. It is just you take sum up to n that increases to 1. That's all. That's a finite dimensional projection, and that increases to 1. Okay. So let I take Qn, Qi, let us say I be a maximal family of orthogonal projection with each Qi is equivalent to P. Let us take Q1 equal to P, and Q1 equal to P. You can do that, right? Start with P and then take in the orthogonal complement, things which are equivalent to that, and you get a maximal family like this. Then first claim is I is infinite. Okay, for that I need the following lemma, which I should have proved it before. The lemma is if PQ in M are finite, this is for any Van Neumann algebra, PQ are any finite for any Van Neumann algebra, then P plus Q is also finite. And P is orthogonal to Q. Okay. P, Q are finite and P is orthogonal to Q, P plus Q. Okay. And proof is simple. So, for that before note, this is a fact. Note, P in M is finite is equivalent to saying this one. This is just a statement. I mean, this is the same statement. PMQ is finite Van Neumann algebra. It just follows that, sorry, PMP. PMP is a Van Neumann algebra on the Hilbert space PH or whatever, and the identity here is P. So P here is finite. That means P does not have a subprojection, proper subprojection, which is not equivalent to that. Okay, and that implies that here the identity is P. So if P has a subprojection which is equivalent to that, then here Q will be here because this contains all those things. I mean, this phenomenon algebra is nothing but all those things that is P x equal to PXP. Okay. So because of that, if there is a Q sub projection of this, then that will be here, and that will be less than that, right? Okay. So that will, so this is clear. Clear exercise. Okay. If P is finite, then this is a finite phenomenon algebra. If this is a finite phenomenon algebra, the identity is this. That has a finite. That it's easy exercise. Okay. So okay. Now we use that theorem. Here is where I want to use that theorem. Okay. Now P is so P is finite means P and P is also finite. So if P, Q both are finite, then P both P and P, Q and P, Q and Q are finite one-dimensional algebras, finite factors, finite one-dimensional algebras. Okay. Then, so there exists a trace here, there exists a trace here. Okay, call this. So there exists trace P, trace Q on PMP, QMP, QMQ. Okay. Now you just take you can take any convex linear combination. You better take this. Then trace of x equal to trace P of we can take 1 by 2. You can take any convex combination. 1 by P trace of what is that? Trace of PXP, which will be in that phenomenon algebra, and 1 by 2 into trace of QXQ is a trace. Trace on P plus Q, M, P plus Q. So if, so P plus Q, so this is finite. So this is finite. P plus Q, M, P plus Q is finite. It follows from that theorem. Okay. So by induction, any finite sum of orthogonal, mutually orthogonal projection, any finite sum of mutually orthogonal finite projection is finite. So now this lemma is over. Proof of the lemma is over. Now we consider that's a maximal thing. So if I is infinite, proof of the claim. If I is finite, then of course summation Pi, I in I is finite because it's a finite sum. And then 1 minus summation Pi, I in I is infinite. Of course, if this is also finite, then the sum should be finite, which is not the case. We are assuming 1 is infinite. So this should be infinite. So, but in a factor, we are assuming M is a factor. So either this should be not the usual less than or equal to, it's then either summation Pi, this 1 minus summation 1 Pi, or 1 minus summation Pi is then equal to summation Pi. This is not the less than or equal to, is the curved less than or equal to partial order we used, and which is a total order. We have proved it's a total order on a factor, since this is a total order on factor, right? Factor. We have proved this is a total order on a factor. So because of that, either this should hold or that should hold. But this cannot hold. This is an infinite projection. We have also proved that if you have an infinite projection under a projection, that projection also infinite. We have proved that. So if if this is true, then this is not possible. Okay. Then that will be this will be an infinite projection, which is not the case. So this will be this. Oh, you don't need summation Pi. You can take Pi. Sorry, Pi itself. No, then Pi is less than or equal to this, or this is less than or equal. So you don't want to. You only want Pi, no, right? P1. P1 or P, whatever, P1, Q1 equal to P, no? Oh, sorry, I have used Q, no? I mean, consciously used Q, but I changed to P. I'm sorry. This will be QA. You have changed. Let QA be the maximal thing. Here it should be QA, sorry. Summation QA. Okay, and P is the Q1 equal to P, that's what we have assumed. Okay, then this P is either less than or equal to this, or this is less than or equal to P. Okay, but then this is not possible, so this is only possible. Okay, so there exists a P, so there exists something equivalent to P, which is less than this, because this contradicts maximality. So this is I is infinite. Okay, hence the claim. Very difficult to write English sentence than mathematics. Symbols we can easily write. Writing a sentence take a long time. Okay. So the I is infinite. So we assume it cannot be uncountable. So it's countable. Okay. Let Qn n equal to 1 to infinity be Qn orthogonal to Qm if n not equal to m, and Qn is all equal to P. Okay. You started with a P and it's all equal to, you have got a countable family. Okay, finally. So, and let Q equal to summation Qn. Yeah. No, Q equal to 1 minus summation Qn, n equal to 1 to infinity, equal to Q. We want to prove, we want to get projection, this may not be. We want to get projection Pn such that summation Pn equal to 1. So 1 minus Qn equal to this. Okay. Now what? Now Q is this. Again, you have a P and Q. You started with the P. Okay. Now either P and Q you have. Q is this 1 minus this. But it's a factor. So either P should be less than Q, Q should be less than P. But P should be less than Q is not possible because you have taken already the maximal family. This is a maximal family. So in the orthogonal complement, you cannot find something equivalent to P. You cannot find it. Something. This is a projection. Under this projection, if you have a projection equivalent to P, then this will contradict the maximality. So that is not so big due to maximality. Okay. Due to maximality. So due to maximality, Q is less than or equal to P. Either this should be less than or equal to, or that should be that by total order, but this should be the case. So Q is less than or equal to P. Okay, that's okay. So what do you want to do? So identity 1 equal to Q plus summation Qn n equal to 1 to infinity. Okay. Okay. Yeah, here comes something. Note. Summation n equal to 1 to infinity Qn. This is of course sum of orthogonal projection, which is a projection, is equivalent to summation n equal to 2 to infinity Qn. Is that clear? We have ui, which takes pi Qn to Qn plus 1. They are equivalent, right? Okay. And you have a set n equal to, I mean, you Qi to Qi plus 1. Okay. Where I equal to 1 to infinity, whatever. Okay. Whatever. Qn or ui. Now, if you have orthogonal projection, something summing to something, you have another set of orthogonal projection where they are intertwined by an partial isometry, then this sum of orthogonal can be equivalent to sum of that, right? So because of that, then direct sum of ua is defined on the domain. Ua is defined on the range of Qi, and the ua's range is initial projection. Every partial isometry has initial projection and final projection. Initial projection of ua is Qi. Final projection is Qi plus 1. Okay. So direct sum of ui, where you define ui on, this was earlier we discussed. Okay. So it's not exactly direct sum, but it's defined on the direct sum. It is the direct sum of Qi. that will take it to, so it's clearly that n equal to 1 to infinity Qn is equivalent to n equal to 2 to infinity Qn. Okay. Because of this, this is equivalent to, this is equivalent to, I mean, this is equivalent to this. So this is equal to Q plus summation n equal to 2 to infinity Qn, right? Because this is equivalent to this, and that is, I'm just keeping it as it is. Now Q is less than P. So this will be less than P plus n equal to Q, P is Q1, okay? P is Q1. Q1, n equal to 2 to infinity Qn. Okay, this is just the sum n equal to 1 to infinity. Of course, this should be less than 1 by definition. Everything is less than 1. Okay. So this implies, but this is a partial order. Okay, this whatever curved less than or equal to is a partial order. So this implies 1 is equivalent to direct sum, this sum. Okay, this direct sum of orthogonal projections. Qn. 1 is equivalent to this. So there exists a partial isometry. I mean, here it's an isometry because it's 1. Direction isometry. Let me use U, capital U for isometry, such that U star U equal 1 and U star equal to summation Qn. Okay. Now define, I want the following. If I take U star QAU, now define PI to be, so I mean, this is okay. I can take UI, U star QI, U. Okay. Okay. Then summation Pn, n equal to 1 to infinity, or Pi or whatever, Pn equal to, okay. That is equal to U star summation Qn. This U is a nice map. When you have a summation, you can take it inside. As I said, X going to U, X, U star. This is a map which is, I mean, there is no other better, nice isomorphism than this. If you have a strong convergence, you can take it, strong convergence. You can take norm convergence, you can take it. This is summation is basically strong convergence. So you can take it inside. Okay. So because of that, this is true. You can take the summation inside. U star U. Now U is an isometry. It acts on H and its range is the summation Qn. Okay. And then U star will take it back to identity. So this is identity. Okay. U from H will take to summation Qn H. Okay. And U star. So when you add summation Qn, it will be identity on this. When you take it, so verify this. Okay. You can verify this. So again, it will take to U star will take it to H. So it's just identity. You can apply Xi here, U Xi, and what will happen, you can check, and it will be this. Okay. So because of this. This is just U star, no? This is just U star. So U star, this is just U star, right? So U star U is identity if you want. Directly check. Okay. That's also okay. Directly you can write. This is equal to U star. Okay. You just insert U star, U star U star U, so you get identity. Okay. So this is equal to 1. Now take Ui, small ui equal to Pi U. Pi U, right? Yeah. Okay. Then this is a partial isometry. You can verify. You have to verify that. I mean, it's clear. It will be. We will verify. You have to show that U star UA star UI is projection. Then UA star UI equal to U star Pi U, right? And that is equal to no, sorry, QA, please. QA. Okay. Now this will be Pi, right? You have QA and you will take it to the summation Qn. When you act on Qi, it will become Qi. If you take a xi, u xi will be in summation Qn in this space H. If you apply Qa on that, it will be Qa on that. But U star will act, it will bring it back to that. Maybe I should write it clearly. This is equal to Pn, that's what I want to write. Qi. Okay, that's right. Yeah. U star Qi. This is equal to U star I mean, you can just insert a summation Qn if you want. U star summation Qn, Qi, summation Qn, Qi, U. Okay. That will give you, then you, I mean, this is just U star and U star Qi. I just want to get, I want to use this direct relation and get Pi. And I want to say that Ui star, which is equal to Qi, U star, Qi, right? And which is equal to Q. This is clear. Summation Qi, summation Qn, Qi. This is equal to Qi, of course, because this is a bigger projection. When you hit it, you will get Qi. This way is clear. And Ui star Ui equal to Ui star Ui in the middle Qi. That will become so Ui star Ui equal to Qi, and Ui star Ui. This I would get Pi. How is Pi defined? Pi is, this is how Pi is defined, no? Pn is just defined like that. So this is Pi. It's clear. Sorry, this is how I have defined Pn. Okay, so Ui star, this is equal to this. So this implies all these Pn's are equal to Qn, which is equal to P. Okay, now summation Pn equal to that we have already seen, which is equal to 1. That's what we want. So we have got a family of projections Pn, where each Pn is equivalent to P and summation Pn equal to 1. You may get something Qn which may not add up to identity, but then using the equivalence of projection, you will get this. Okay. Now here comes the final statement. Maybe a theorem. This theorem just says a 2 infinity factor is nothing but a tensor product of a 2-1 factor and a type 2-1 factor. So type 1 factor. Okay. So type 1 infinity factor. If you know 1 infinity, no, type 1 factor. It can be finite also. So before the live, let me define what is a tensor product. I haven't said. Suppose M1 is contained in B of H1, M2 contained in B of H2, or one and algebras. Okay. Then define M1 tensor M2, which is contained in B of H1 tensor H2. You can take Hilbert space tensor product, which is defined in B of that. And in that, you define it to be equal to, you take all such x tensor Y, where X is in M1, Y is in M2. Okay. And then you take the double combinatorial. That's all. This is very easy for a one-dimensional algebra. For C-star algebra, actually it's difficult. Okay. And there are many tensor products also. So this is clear. Okay. So this is a tensor product of fundamental. This will be, of course, by definition, this is a fundamental algebra. And that is what you call as tensor product. So M is a 2-1 factor, sorry, 2 infinity factor. Okay. And P in M is a finite projection. It certainly admits one finite projection. Oh, it will be infinity, sorry. It has to be infinity, otherwise it will be, no, if you have a m and if you tensor with mn, it will be again finite. So that will give finite, that will be again to one factor only. It has to be infinity, okay? Then m is isomorphic to, I mean, m is isomorphic to PMP. I'm saying P, writing Q. So if P is a finite projection, so PMP is a 2-1 factor. Okay, it's tensor B of L2. That is, I say, I mean, we will write the isomorphism explicitly. There exists a U from PH, where this is in B of H, as you know. PH tensor L2N, these are Hilbert spaces, okay, to H, okay, such that U of this PMP is sitting here, okay, tensor B of this, whole of this, L2N, U star is equal to N. Okay. Proof. Choose Pn and all those Pn are equivalent to P, where you have the family given by the earlier proposition, okay, and choose partially symmetry Ui such that Ui star Ui equal to P1 or whatever P1 or P1 equal to P, okay, you take your P1 equal to P, or you change your P, take something, okay, it doesn't matter. P and Ui star equal to Pi. They are all equivalent. Now define U. We will write it there. Define U from whatever the Hilbert space. PH tensor L2M, L2N, 2H by. So how is anything? L2N is a infinite matrix of scalars. No, infinite numbers, sorry, numbers. So where this, where U of xi tensor to take a sequence lambda n, okay, equal to summation lambda n Ui xi, right? See this I mean summation Pn equal to 1. So H will be written as direct sum of n equal to 1 to infinity Pn H, right? Summation Pn equal to 1 and Pn's are mutually orthogonal. So H will look like this. So any xi here will be direct sum of xi n. Now this Ui xi, this is scalar. Un xi. Un is a partial isometry which intertwines P1 and Pn. Okay. So range space of Un will be the Pn, range of Pn. Range when Un has initial space range of P1 and final space range of Pn. So Unzi will be in Pn, Pnh. Okay, so this is an orthogonal direct sum of that. And if we have done this for type 1 factor, same calculation will tell you that U is unitary. Okay, and you can see that U of any vector, any X tensor T, X is in PMP and T is in V of L2M, will U star will be equal to summation. It is just the, with respect to this, see this H is direct sum of this. So H is like matrices containing operators on this, right? Is that okay? I mean, if you have a direct sum of two things, you will write it as a 2 cross 2 matrix containing operators other than scalars. If it is C direct sum C, which is C2, then you have direct sum of scalars. I mean, you have matrices of scalars. If you have direct sum of Hilbert space, you will have a direct sum where you will have a matrix where each entry is an operator between the corresponding Hilbert space. Okay. So this is equal to, this will be Ui X Uj star, where X is in PMP. Uj star will bring from Pjth vector, Pjh to P1. So X will act on that. And then it will take it to Pth one. So it's something like this. And that map is clearly thing. And you can see that these kind of things are strongly dense here, and these kind of things are strongly. I mean, any X in any X in B of H is actually, this is in the form of Pi. This is also, I mean, you can verify that Ui X Uj star is nothing but Pi X Pj also, because U's are the corresponding partial isometries. Okay. You verify this. Okay. This we have done it already in the type 1 classification. Okay, it's the same thing. Okay, so because of, so now any matrix X in B of H, X is equal to Xij, whereas Xij is nothing but Pi X Pj. That's all. Or you can even write it as X is equal to summation Pi X Pj. Okay, you can summation Pj equal to 1, summation Pi equal to 1, summation Pj equal to 1. The sum is over I and j. This is the matrix form of this, if you want, or whatever. It is just you have to write and then get convinced. Okay? And these kind of vectors are strongly dense in M. These kind of things are strongly dense here, right? Strongly dense in this tensor product. Okay, by definition. Okay, so you will map this to this. U is a nice map. Take strong closure to strong closure. So because of that, this will be the isomorphism. So we have proved that the 2 infinity factor is just a tensor product of a 2-1 factor and a type 2 1 infinity factor. 1 infinity means the H is infinite. If it is finite, it will give it out type 1 only, because you can define a trace again on that using that, right? If you have finite means everything will look like some X, I mean, summation, I mean, it will be like Xij kind of thing. So you can define the Xii, summation Xii will be a trace on this. Right? If you have a M is a type 1 factor, and if you take tensor M and C, okay, so any element here will be a matrix like Mij. You can actually verify it will be like this. You can define a trace on the summation Mii, a summation trace of Mii, sorry, where trace is the original trace on M. So because of that, it will give a 2-1 factor. So you have to take in tensor with B of H, I mean B of type infinite Hilbert space. Okay. Okay. So this is on type 2 infinity. So the final thing I want to say is this is just I'm just going to mention it, how you do this. Or I will give you a hint how to get a Fields medal, maybe. I'll give you an open problem. If you solve it, I'm not sure whether you will get a Fields medal, but you deserve one if you solve this. Or some other good prize you will get if you solve the problem I mentioned here. Huh? I'm going to say no. So, I mean, the problem is the following. We defined gamma of G, right? Okay, gamma of S infinity we have defined. And for infinite conjugation class, these are the examples we have. S infinity and the free group, right? Fn is a free group in n words. Okay, n letters, free group in n letter, word in n letter. This is a free group of n letters, Fn. So we can define S infinity. One can prove that a gamma of S infinity is not isomorphic to gamma of Fn. One can prove. The reason is this is what is called a hyperfinite factor. I will mention it in the next one. Hyperfinite to one. These are all to one factors, of course. They are all to one. This is hyperfinite to one factor. This will not be hyperfinite. So because of that, they are not isomorphic. So the question is whether gamma of Fn is not isomorphic to gamma of Fm if n not equal to n. So, I mean, recently I have been looking at, but I'm sure this is not solved. Okay. Recently, very recently, I have been looking at what's happening in the archive, but so I'm 100% sure this is not solved. Okay. To solve this problem, someone called Vaculescu introduced what is called free probability. The probability we are doing in the usual classical probability is the commutative one, whatever it means, which I have mentioned. The non-commutative ones are whatever, using these projections of other things. So the highest kind of non-commutative is what is called free probability. There is no commutation at all. Okay? So free probability is what was introduced by Vaculescu. And it's very, I mean, it's a ocean now. There are too many things done in that. But the original problem is not yet solved. Okay? So introduce that to solve this problem, which is not solved yet. So don't take it as a PhD problem, but if you solve it, okay, you will be awarded. Okay, so okay, so if you have consider this M2, M2C, okay, this sits inside M2C, tensor M2C, which is of course M4C, M4C or M2 power 2 square C, like X going to X tensor 1. This is, I mean, it has to be unital. The embedding should be unital. Okay, it cannot sit as X direction something 0 or something. It cannot sit like this. Okay, it has to sit with as X tensor 1. Okay? This is how it sits. So in this way, M2 power n will sit inside M2 power m C. Okay. Okay. So where this will be kind of m is greater than n. Okay. Where in the first nth places it will sit like that, n tensor 1. Okay. Which is again X of the first n places tensor 1. This is M2 tensor, M2 tensor, M2 tensor m times. This is M2 tensor n times. So first n places tensor, n tensors it is X, and the remaining thing is 1. Now you choose this A naught. This is equal to all those X1 tensor, infinite tensor like this. I mean, both sides. Infinite, both sides, no, one side is X1 tensor, X2 tensor, infinite tensor like that, where Xi equal to 1, except for finitely many, except finitely many. Only finitely many you have. So all this M2n, this is just an algebra. Okay, we are not treating it as M2n is sitting inside this A. As you take the first n of them as X, I mean, first n of them as that element, and the rest is 1. Okay. Now you have a trace on this. You can define the trace of any X tensor, whatever. X is a big thing, but finitely many. Then 1 tensor, 1 tensor, 1 tensor 1 after some time. Okay. This is equal to trace of X. Trace of X is defined it will sit in some M2n, but then this is well defined because the trace on M2m restricted to M2n is basically the trace on M2n. Okay, so this trace will be well defined. Okay, so you will get a trace on this. Just a tracial state on this A. Now you construct the GNS construction. This is not a C-star algebra yet. You can actually have C-star algebra, but then I have to talk about inductive limit or something. But you don't worry about it. You just take this algebra A. Then you take the trace. Using the trace, you define the inner product in the GNS construction. Same thing. Okay? If you do all that, you will get a Hilbert space H corresponding to this A. Okay, define using the trace, define an inner product on this. That will give a pre-Hilbert space. That will give you a semi-Hilbert space. semi-inner product on that, quotient it, then you get a, I mean, if it is faithful, it will be inner product space. Okay? You assume it will be faithful. Okay. So because we are starting with the faithful trace, so it will be a trace on this. So you just using the trace, you define this trace of x star y, okay, on this, inner product on this, inner product of y star x. This is a mathematics problem. Okay. You have this. Now you have a Hilbert space on this. Then this A will act on this Hilbert space as operators. Okay. Then you define M is equal to A double compta. Okay. This M will be a 2-1 factor because there will be a trace on the dense subspace which you can extend it. Indeed, that will be given by the vacuum vector. The trace will be given by the vacuum vector, so it will be strongly continuous. Okay. I will just say all these things because it's not part of exam. So I'm just telling you. So this M, now this M will be inside this H, B of HA. Okay. And you have a cyclic vector. This is genus one. You have a cyclic vector. That cyclic vector will evaluate the trace on that. Okay. And that will be a trace on this. And that trace is unique because all these traces are unique. When the trace is unique, it will be a factor. Did I say this anywhere? But you can verify. If a trace is unique on a one-dimensional algebra M, then it's a factor. If it's not a factor, there will be, you can take direct sum and you can use the cyclic convex combination of, forgetting words, convex combination of traces, and you get a different traces. Convex combination you can use for any lambda, you get different traces. So if the trace is unique, if there does not exist two traces, then it's a factor. But here the trace is unique because all those traces, everything, the way you have defined is that is the only trace. Because of that, this M will be a factor. It is a 2-1 factor because there is a trace. So M will be a 2-1 factor. This factor will be isomorphic to this gamma of S infinity. Because that is a big theory. This is what is called a hyperfinite factor. In the sense that there exists finite dimensional algebras. You have finite dimensional algebras. All this is finitely many of the M2N. This A is a union of finite dimensional algebra. It's a union, right? Increasing union of finite dimensional algebra. So increasing union of finite dimensional algebra is dense here. That is what is called a hyperfinite factor. Okay, and that B of that the gamma of F2, F3, Fn, that will not be hyperfinite. Okay, so this will be a hyperfinite factor. So here you are trying trace. Instead, this is just one word I would say. Take P lambda of X equal to where X is in M2. Okay, and X equal to X ABCD. Okay, equal to 1 plus lambda A plus lambda by 1 plus lambda B. And lambda is not equal to 1. If you take lambda equal to 1, this is half of A, this is half of B, which is trace. So you don't take a trace. It is just you take some lambda. D, right, correct. D, yeah, this way, D. Okay. This will give rise to type 3 factors. And they are hyperfinite, of course, they will be finitely. I mean, this, you do the same construction. You do the same construction, embed it like this and take the A, which is union of all that. Instead of trace, use this state to use the GNS construction to get a factor like that. Okay. Then that will be a type 3 factor. And they are not isomorphic. If lambda 1 is not equal to lambda 2, they are not isomorphic. They are different. So you get a continuum where lambda is in 0, 1. Okay. You get a continuum of factors, hyperfinite factors. They are not isomorphic when lambda 1 is not equal to lambda 2. Okay. And uncountably many of them. They are all hyperfinite. And they are all type 3. So this is how type 3 factors are constructed. This was constructed by Powers. I mean, this was a path-breaking result because after Van Neumann, John Van Neumann and Murray Van Neumann, they defined all that. There was only one, they were able to construct only one type 3 factor. For a long time, that was the only example. Okay. Then in the 60s, mid-60s, I'm not sure about the year, Powers came with this construction, which is very easy, which is not difficult. To prove it's type 3 and all that difficult, of course. So he with this construction, he got this continuum of type 3 factors. Then there is a very rich theme after that. Okay. So that's all. So this is a, so the reference is, one reference is Sundar's book, Invitation to Phenomenal Algebra, or you can look at Jones' book is there. It's not published as far as I know. Jones died. So the PDF is available in the internet. You can just search for it, you will get it. Okay. And I have taken the finite projection, all that from that book, the later part. Okay. This, I think this is maybe mentioned there. I don't know. Some of them will be there, some of them will not be there. I'm not sure. But mostly you will find it in that book.